Hello, this is Brian Washburn. I like to do a coupled oscillator problem. And this is a very standard kind of cool coupled oscillator problem. So what I have is, and this is example directly from your book, so you should look there for further illumination. I don't know. Anyhow, so let's take a look. So what I have is I have two masses, and it's on a frictionless surface. There are three springs connecting two masses. Okay. And then I'm going to call a generalized coordinate x1 is the position of mass m1 with respect to its equilibrium position. x2 is the position of mass m2 with respect to its equilibrium position. And there's three springs, k1, k2, k3. What I'm going to do is I'm going to write first down the equations of motion, assuming that the masses are different and the spring constant are different. And then when I solve it, I'm going to solve it with the same masses and same spring constants. You'll do a homework problem where they're not the same. Okay. So what I'm going to do is I'm going to look at, I'm going to use F equals ma, so I'm going to look at the net force on K1 and K2. So take a look at, or M1, M2, take a look at M1. Well, first of all, if you had first, what force is acting on? Well, the first thing is just the force of the spring of constant K1 minus Kx, so that just makes sense. The second term, okay, think about this. K2 only acts if there's a difference between x1 and x2. So if x1 and x2 move together, then K2 doesn't stretch at all, and thus it doesn't exhibit a force. So one way you think about it, just like an EP, right? Forces only act on a mass if it touches it. So this, for example, spring K3 doesn't act on M1 because it doesn't physically touch it. It only physically touches M2. So if x1 and x2 move in the same direction, say they move left, but don't change the stretch of K2, then it won't act a force. The only time you're going to get a force acting on it, there's a difference between those lengths. So that's why they have this thing here. And by the way, it has a plus sign because it's going to pull in the opposite direction than the spring constant K1. Similar arguments could be said about all the forces acting on M2. Notice that there's no K1 here because K1 doesn't touch mass M2. So again, K3 causes it to, that's a restoring force, okay? And then again with K2 only has a stretch there if there's a difference between x1 and x2, okay? All right. Okay, so what I'm going to do is instead of writing, I'm going to write these guys as something times x1 and something times x2. So using this net force, I can just rewrite it as mass times acceleration, acceleration of mass 1, mass 1, acceleration of mass 1. And then I have k1 plus k2 times x1, and then k2 times x2. And I can do the same thing there, okay? All right, now I can rewrite these equations as a set of coupled equations. And remember, the method is what I want to do is I want to write these coupled equations in the form of a matrix M x double dot is equal to k x, where again, where x in our case is going to be equal to x1, x2. X double dot is just the derivative, second derivative of that. Now, what's M going to be? Well, just looking at it, you can M is just going to be our matrix, our mass matrix, M1, 0, M2. And you can see that because on this side I have M times this. Well, in order to get this thing here, my matrix has to look like that. And then K is going to be a spring constant matrix. And what I'm going to get here is K1, K2, minus K2, minus K2, K2 K plus K3. Okay. Now, what's significant about this K is the off-diagonal terms. The off-diagonal terms is, notice it's minus K2, or K2 just by itself. K2 is a coupling spring. Okay, what does that mean? Well, if I were to snip K2 there, all right, then this would oscillate independent of that. But K2, when it's there, it couples the system, okay? And that's what makes the coupled oscillator. That will be the off-diagonal terms, and that's true for any kind of coupled oscillator problem. The off-diagonal terms are the things that couple the two oscillators. Okay, So now, all right. So now let's find the normal modes, the normal frequencies, and the normal modes. And so I'm going to do it for a simplified case where M1 is equal to M2, which is equal to M, or defined as M. K1 is equal to K2, equal to K3, which I'm going to define as K. Okay. Now, that simplifies my matrices. M is just going to be equal to M00M. K is equal to, well, 2K minus K minus K, 2K. And now I want to find the eigenvalues of the matrix. Well, I want to look for well, let's say it this way. I want to find the determinant of the matrix K omega squared M. I want to find the determinant of that. I want to set that equal to 0 and find that. Okay, so let's just do that. Okay, so again, my solving the eigenfrequencies is equivalent, we showed this, to basically finding this thing, the determinant of that is equal to 0. All right, let's first write down what is this. Okay, well, that's going to be equal to 2K minus omega squared M. And then I have minus K, and then 2K omega squared M. Okay, let's find the determinant of that. Well, I just multiply this times this minus this times that, set the determinant equal to 0. If I do that, the determinant of this thing here equal to 0 gives me an equation that looks like 2K M omega squared quantity squared minus K squared is equal to 0. I can factor out the roots. I'm going to get Km omega squared 3K minus M omega squared. Now notice, when I actually multiply that through, I'm going to get a quartic equation, just like we did before. Nothing wrong with that. But in the end, I'm going to get two distinct roots. I'm going to call these roots, well, let me call this omega symmetric, which is going to be K over M. And then omega anti-symmetric, which is going to be equal to 3K over M. But notice that's equal to the square root of 3 omega symmetric. So notice that now this cool thing, notice the anti-symmetric mode looks like just one mass spring system, K over M. Okay, we'll explain that in a little bit. The anti-symmetric mode is root 3 times the symmetric mode. It's actually, again, larger than the symmetric mode. So those are the eigenvalues. Okay. So we know how the system is going to oscillate. It's going to have two fundamental frequencies of oscillation, but we don't know exactly just yet how it's going to oscillate. Okay. So in order to do that, we got to find the eigenvectors. So let's do that next. Okay, so let me find the eigenvector. Now the eigenvectors have a name. They're called the normal modes. And let's find the normal mode for the normal frequency omega symmetric, which is going to be equal to K over M. All right. So what I'm going to do is I'm going to stick omega 1 into this matrix equation that looks like this. Okay, I'm going to multiply that through. If I multiply that through, I'm going to get K minus K minus K, K. Okay. Now, remember what we had in our vector, our matrix equation. Our matrix equation looked like this. That times A is equal to 0. So that must mean, now I can get the K's out. That must mean that 1 minus 1, or let me write it this way. K minus K, K minus K, K minus K, K times A, it was A1, A2, remember, A1, A2 are complex things, equals 0. So I can get rid of the k's. That's going to give me 1 minus 1, minus 1, 1, times A1, A2 is equal to 0. So that gives me two equations, two unknowns. From one of those equations, I get A1 minus A2 is equal to 0. Okay. And I get the same equation from the other one. That must mean that A1 is equal to A2. And I'm going to write that as an amplitude in the phase. Instead of using alpha, I'm going to use big A e to the I delta. Okay. So what does that mean? Z of t is equal to A1, A2 e to the I. Again, we're assuming simple harmonic motion, and that's omega 1. Well, that's going to be equal to A e to the I omega 1 t. Now you may say, well, what about that delta and what about the A? Well, that depends on my initial conditions. Again, I'm solving a second order differential equations. My two unknowns are A and delta. Okay, that's Z. I want now X. X is the real part of that. X of t is going to be equal to, well, is going to be equal to A, okay, cosine of omega 1 t minus delta. So my solutions, x1 of t is equal to A cosine omega t minus delta. And x2 of t is the same damn thing. Okay, I called it omega 1, but let's call this omega symmetric. Okay, so what's going on there? Well, if you plot, you know, sorry about that. It's hard to draw a straight line on this stupid thing. All right, so I got here, this is time. Here's x1, here's x2. Well, basically, as a function of time, they're going to be in phase with each other. That's the best I could do. Okay. So they're going to oscillate in phase. Now, you think about this. Now, notice that the normal frequency is k over m. You know, you may say, why is that k over m? It looks like just like a simple system. Well, if the two masses x1 x2 move together, you don't change the spring length k2, and so it just all it does is, so basically it never stretches or expands. So basically these two masses just move together with each other, and they kind of look like one big spring. Example is this. So basically, remember, here's kind of this kind of pictorial thing. So I got, you know, here's this, here's mass 1, that thing there. Okay. And so then what happens is this whole thing, you know, this distance never changes. So it kind of looks like a big mass like that, like that. And so then that's why it kind of looks like just the motion of a single mass, okay? Because this distance between M1 and M2 never changes, okay? This is K2, all right? So that's what's going on there. Okay, now what we're going to do is let's look at the second normal mode, all right? And so the second normal mode, that's the anti-symmetric mode. And we want to look at what's the motion. And again, we're going to find the eigenvectors associated. So the second mode, which I'm calling omega A, that's called the anti-symmetric mode. And I think you can guess what it's going to look like. Okay, that's what it is. So I'm going to do the same thing. I'm going to set K omega anti-symmetric squared M. If I do all that, I get a matrix that looks like minus k, minus k, minus k, minus k. All right. Now, what I can do is I can put this into the equation k minus omega a squared m times a as a kind of a vector equation. And I get, if I do that, I get, well, I'm going to divide by k's, but I'm going to get 1, or minus k, I should say, 1, 1, 1, 1, a1, a2. Again, two equations, two unknowns. And then from this, I can show that A1 is equal to minus A2. And I'm going to say A1 is equal to A e to the I. Same thing that they did before. So now let's write down Z. Z, again, Z is a column vector. It's going to be equal to A1, A2, e to the I, omega antisymmetric T. That's going to be equal to A minus A e to the I omega antisymmetric delta. I forgot the T there. Okay. Now X is going to be the real part of all that. And that's X1 as a function of time, X2 as a function of time. And that's going to be equal to A minus A cosine of omega antisymmetric T minus delta. Okay, so notice that now, just write out the solution. So x of x1 of t is going to be equal to A cosine omega antisymmetric minus delta. Again, A and delta depend on my initial conditions. But x2 is 180 degrees out of phase, minus sign, minus 1. Okay. So what's happening there? Well, what happens there, if we just plot out those solutions again, we have here time, sorry, apologize for that, time, x1, x2, this looks like cosine, this looks like minus cosine. It's hard to draw cosine on this. Okay, they are pi or 180 degrees out of phase of each other. That's called the anti-symmetric mode, because what happens is, back to my oscillator system here, basically have this. Now in this case, this spring does compress. So when this one goes this way a distance, this one goes this way a distance. And then when this one goes out, this one goes out equally. So it kind of goes opposite. And that's anti-symmetric to each other, kind of mirror images of each other with respect to the middle of the figure. So obviously there, all the springs are being compressed and expanding. Okay, so notice what we've done is we've solved, we've got a column vector for the symmetric mode, okay, as a function of time, and a column vector for the anti-symmetric mode, okay. Those guys there form a basis set. So given any solution x, I can always write that as a sum of a constant C1 or called CS, depending on my initial conditions, of xs time plus CA XA. So we've completely solved this problem for any initial condition. And so any solution can be written as some linear superposition of the symmetric normal mode and anti-symmetric normal mode. And that's pretty powerful. Okay, so that's a coupled oscillator problem. The homework problems, basically the methodology for solving all these problems is very similar. Again, just to remind you what that is, basically what we do is we find, for any coupled oscillator problem, what we're going to do is we write down kind of the equations of motion. We find a matrix M, we find a matrix K, we take K minus omega squared M, we set the determinant equal to 0, that is equivalent to an eigenvalue problem. We find the solutions of that. The solutions to that are the eigen frequencies, or the eigenvalues, or they're the normal frequencies. And then what we can do is we can stick them back in order to get the normal modes or the symmetric and anti-symmetric solutions. Okay. One other problem, this talk about anti-symmetric and symmetric solutions, is, you know, a problem you're going to be dealing with, and you can play with this in a hall, is we're going to have, you have two penduli with a spring between the two, okay? And you may say, okay, what are the symmetric and anti-symmetric motions for that? Well, you can pretty much guess what they're going to be. The symmetric motion is going to be a motion that kind of looks like this, where they move, and the length of the spring doesn't change. So basically, this moves together and back and forth. So they both kind of swing, and I'm going to get some symmetric oscillation from that. Okay. And then what's the anti-symmetric going to look like? Well, the anti-symmetric motion kind of does, one's going to be like this, one's going to be like that. Spring will be stretched, and then at some later time, they're going to be like this. Okay, so that's going between those two there, versus motion where, let me erase, you know, basically for the symmetric oscillation I have something that looks like that, and then at a later time I have something that looks like that. Okay. Now, there's also one other cool thing to do with the double pendulum, which you can get from solving these equations, is, and you should do this, okay? What you do is you take one pendulum and hang it, do this in the hall, and then what you do is you take the other pendulum to start like that, and then let it oscillate and see what happens. It's pretty cool. So if we have time, we'll talk about that in class. All right, take care. Bye-bye.